For this lesson, we're looking at impulse and momentum. So this is our Module 9, Lesson 1. So we're going to be able to understand momentum and impulse, both linear and angular, in those two systems, and how they're related to impulse momentum. And we're going to understand that applying a force to an object over time changes its momentum. So this piece right here kind of goes with our impulse momentum theorem. Okay? So our bell ringer question to look at. So cars are made to brake easier when you get in an accident. Why are cars made that way? So why are cars made to crush or crumple upon impact during a collision? Okay, if you didn't know that, then you can look it up and kind of get yourself an answer. So they're actually made this way to increase the time of the collision. So our impulse momentum theorem here talks about force and time creating what is called an impulse. So that'd be the impulse of the collision. If we have a greater time, then we're going to have a lesser force. So they practice this stuff. They look at test dummies. All right, so I'm not going to read through this. You can read through this if you want to. So you have a test dummy. The car is going to crumple, and we're going to have the airbags go off. So that's going to increase the time it takes for the dummy to stop. If we can make the most time possible for that dummy to stop, or for the person to stop in the real life scenario, then the force is going to be much less, and we have a greater chance of survival depending on the force on our body. Okay, so that's why cars are made to crush or crumple upon impact. So let's jump ahead. So we kind of answered this question already, how do airbags work to save lives? So that would be the cars crush and the airbags go off. That's going to increase our time even more. All right, so we'll kind of answer that when we talk about impulse momentum. And so there are some vocabulary words that we're going to be taking care of. So impulse momentum, and then the theorem, and then the angular version of that as well. So what is the impulse momentum theorem? So impulse in general on an object is the product or the multiplication of the force times the time. So we have a force exerted on an object over a time, right? So if a baseball player hits a baseball, the baseball is not going to take that long to bounce off the bat, right? So we're going to have a pretty serious force involved there in a pretty short time. Now, if we had a rubber ball, okay, so like a rubber baseball, or maybe like a bouncy ball, or maybe like just an inflated ball, then you guys know that it takes a lot more to get that ball to fly the same as a baseball. Well, that's because the amount of time involved with hitting that ball is a lot more because it compresses on the bat. So our measurement or our label for impulse is Newton seconds. So impulse is going to be force over time. So force times the change in time. That's the impulse of an object, and it's going to come into play here with our actual formula here coming up, or our theorem coming up. But the next thing we have to take care of is the momentum of an object, and hopefully you remember this from your previous classes. So momentum is the product of an object's mass times the object's velocity. So momentum is just moving mass. Okay, so if you went up to somebody and asked them what is momentum, well, they can tell you that they could probably give you a scenario where they say if a little football player versus a big football player is running, the big football player is going to have more momentum because it has a greater mass. So momentum is a mass times an object's velocity. Okay, so momentum, if we think about the scalars and vectors, momentum is a vector because velocity is a vector. So we're going to have a direction with that momentum. It could be forwards or it could be backwards, depending on the change, right? Okay, so the labels for momentum is kilograms times meters per second, and we can get that by just looking at our basic momentum equation. Mass is measured in kilograms, and velocity is measured in meters per second. So momentum is kilograms times meters per second. All right, not too complicated. So a thing to note here, momentum and velocity are not the same, okay? And hopefully you know that because of the equation here. Momentum includes mass, okay? Velocity is just going to be how fast something is moving, and momentum is going to be how fast that mass is moving. So it's going to be a different quantity. Okay? So taking it to the next step here, we have the impulse momentum theorem. Okay, so the impulse momentum theorem states that an impulse on an object is equal to the change in its momentum. And here is our theorem below. Okay, so I mentioned that in the last slide. Momentum, or impulse, excuse me, impulse is a force over a time. And we can relate those to the momentum of the object. Okay, so this is the change in the momentum of the object. We can also write this as F delta t equals delta p. So that's the change in momentum, which is the same thing there. So if we have a larger force involved sometimes, then we're going to have a smaller time. Now, if we talk about collisions here, we're going to get to that eventually, but with collisions, impulse is the same. Okay, so impulse is the same between two objects. Alright, and that's going to be kind of interesting piece here once we talk about collisions between two objects, but impulse is always the same in a certain scenario. Okay, so let's think about this. Below here we have a diagram, so let's see if we can figure this out. So for this diagram we're just going to solve in terms of velocity and solve in terms of momentum. So in terms of velocity, this is a little bit different because we have a mass times a final velocity minus a mass times an initial velocity. That's how we get those momentums, right? So we can relate those two. So a little bit of algebra tells me that I can factor out that mass, and I'll get final velocity minus initial velocity, which would just be mass times change in velocity. Okay, so if I wanted to get this in terms of velocity here, I would have to divide the mass out. So it would be F delta t over m, and that's going to be my change in velocity. And here we can write that as our change in momentum. Okay, so these are two variations of the equation that we can have if you wanted to have these in your equation bank. However, I think it's easier just to remember our original impulse momentum theorem that we have written up above. So here's two variations that we could use if we wanted to. So let's see if we can figure out how impulse momentum theorem relates to things in the chart below. Let's see if we can put this together. Okay, so this is kind of on the left side of the equation. We have F delta t, so this could be the impulse on an object, which is the product of the force and the time. Now on the right hand side of the equation we have that, which is the change in the momentum of the object, which is the product of the mass and the change in velocity. Okay, or we could just write velocity. So this kind of takes us back to our variations in the equations in the last slide. So if we were to look graphically at the impulse of an object, then usually we're going to have a force time graph. Okay, and if we want to find the impulse of that object, then we would have to find the area under the curve. Okay, now my class is an algebra-based physics, so we would not be able to calculate that very accurately, but if you wanted to calculate the area under this type of curve, then you would need some calculus and you'd be using integrals from 2 points. So in this scenario it'd be from 0 to 1.5. Okay, so integrals would calculate the area under the curve, which would give us the impulse of this scenario here. Looking at an example of momentum here, we're going to look at the impulse momentum theorem and just kind of momentum in general. So it'll kind of kill two birds with one stone here. So we have a 2,200 kilogram vehicle traveling 94 kilometers an hour, which is 26 meters per second. It can be stopped in 21 seconds by a gentle applying of the brakes. It can be stopped in 3.8 seconds if the driver slammed on the brake, or it can be 0.22 seconds if it hits a concrete wall. So what is the impulse exerted on the vehicle, the average force exerted on the vehicle in each of these stops? So we have three different scenarios. Scenario 1, which is the gentle braking. And then we have scenario 2, which is the hard braking. And then we have scenario 3, which is the wall. Okay, but this is going to give us some good practice with momentum and impulse. So in each of the scenarios, we have an initial momentum we have to figure out. So it's going to be the same here. So remember, momentum is just moving mass. So momentum is signified by P, and that's mass times velocity. And then we can also have like an initial momentum, whatever we get for that, and then we'll have a final momentum after the object stops or when it crashes or something like that. If it is stopping or something like that, then this could be 0 because momentum is mass times velocity. If your mass is not moving, your velocity is 0, then your final velocity would be 0 here. Okay? So in each of these scenarios, we are stopping. So we're going to have a final momentum of 0, and since it's mass, moving mass, that's kilograms times meters per second for momentum. And that's going to be the same across the board here. And then we have an initial momentum, which is just going to be the mass of the vehicle, which is 2,200 kilograms, times its initial velocity that it's moving. So it's the initial velocity, we're going to use the meters per second, because everything needs to be in meters per second, because that's what we use for that label. Okay, so we're going to have 26 meters per second. So we get an initial momentum of 57,200 kilograms times meters per second. Now that's a pretty big number, but remember here we are working with a vehicle. We're working with a car. Okay, so this is our initial momentum there, and that is our final momentum. So in each of these three scenarios, the initial and final momentum are going to be the same, because we're traveling that 26 meters per second and we're coming to a stop. What's going to change in each of these scenarios is the impulse. So impulse is going to be force over time. So the force of the impact over the time of the impact. So you can see in our scenarios we have three different times available. So that will allow us to calculate the force. So oftentimes impulse comes into play when you have vehicles crashing, vehicles stopping, two objects crashing with each other. We want to figure out the average force exerted in that time. Alright? So in general, the impulse is equally exerted on both objects, but what can change is that momentum, right? Because if we have consider we have a small object and a large object, the force between these two, the impulse between these two rather, would be the same if they crashed, but the change in momentum is going to be much greater for this one than it would be that one. So this one would have a little change in momentum, where this one would have a much larger change in momentum. Okay, so that's kind of the trade-off there. So forces and impulses are the same on two objects. Remember that. Okay, so looking back here, let's write our equation. So our impulse momentum theorem is force times delta t equals our change in momentum. Okay, and change in momentum is final momentum minus initial momentum. So we have our times for each one of these scenarios. Okay, so we're going to write that time down for each of our scenarios. That way we have something to plug in. So for scenario 1, it takes us 21 seconds to stop. For scenario 2, it takes us 3.8 seconds to stop. And scenario 3, it's going to take us 0.22 seconds to stop. So this is the one hitting the wall. So that's going to be a really quick stop, fairly quick stop, and a slower stop. Okay, so let's plug it into our equation that I have listed there below. Force times change in time. Usually change in time is 21, like it's just 21 seconds total for this one, however many seconds it takes us to stop. So 21 seconds is going to be change in momentum. So remember we said our final momentum, because we're coming to a stop, is going to be 0. So that would be 0 minus 57,200 kilograms times meters per second. So we can see that in general here, since we're coming to a stop, our force is going to be negative, which makes sense because we're slowing down, or there has to be a force pushing in the opposite direction in order to stop the object. Okay, so to solve this, 0 minus 57,200, that's just going to be that 57,200. So I'm not going to do anything there. I'm just going to divide by 21 seconds. And we get a force of negative 2,723.81. Okay, and that would be in newtons. So that is the force that we're going to get out of this. All right, now I kind of jumped ahead of myself a little bit here because the question that we had to ask here is, what is the impulse exerted on the vehicle? So remember, impulse, I'm kind of writing it out over here, impulse was F delta t. So the impulse here is going to be equal to the change in momentum. Well, the change in momentum is going to be the same for all three scenarios. It's going to be 0 minus 57,200. So that is just a negative 57,200. Okay? And this is usually given in Newton seconds. That's what the label for impulse is. Regardless, I know that, or we know that momentum is kilogram times meters per second. But when we're looking at impulse, we're looking at force times time. So a force times the time would be newtons for the force and seconds for the time. Okay, so this would be the answer to that first question. And that second question, we're going to go back to here and we're going to figure out the rest of these forces involved. Okay, so let's do this second one here. For the second one here, we'll have F delta t, and our delta t is 3.8 seconds. That's going to be equal to that negative 57,200 Newton seconds. All right, and then just like the last one, we would divide out the time, so divide by 3.8 on both sides, and we will get 260,000. So that should be a negative 260,000 newtons. And I also forgot the negative on this one. Since we're slowing down and we're coming to a stop, your force will be negative. Okay, so we can kind of analyze these three scenarios a little bit. We have a force of negative 2,723 here, negative 15,052 here, negative 260,000 here. The thing that changed here was the time. So if we look at how impulse works, if we have a longer time, then we're going to have a smaller force. Okay? So if we have a shorter time or a much smaller time, okay, then we're going to have a much larger force. So we can see we went from 21 seconds to 3.8 seconds, so that's quite a bit different. And our force went from 2,700 to 15,000. Okay? So a much smaller time equaled a much larger force. So a scenario that goes with the first practice problem. We have a passenger of 85 kilogram mass in a vehicle described. For both gentle and hard braking situations, calculate the impulse and average force needed to bring the person to a stop along with the vehicle. Okay? So if we were looking at just the person here, let's say we're looking for the gentle and hard braking, so that would be scenario 1 and scenario 2. So the time for scenario 1 is 21 seconds. Time for scenario 2 is 3.8 seconds. So in this scenario, we're looking at just using the person. We're trying to figure out the momentum on the person here, the impulse on that person. So if we have our momentums here, let's figure out our initial momentum here. So we are going 26 meters per second. So it's mass times velocity, which is 26 meters per second. Okay, so we're going to take that 85 times 26 meters per second, and we get 2,210. And that's kilograms times meters per second for our label. So that's our initial momentum. And in all scenarios here, again, our final momentum is going to be 0 because we are coming to a stop. Okay? So if we want to calculate the impulse, remember that's F delta T equals final minus initial momentum. Well, this is the impulse here, so really we're just looking for delta P, or change in momentum, to get our impulse here. So it's going to be 0 minus 2,210 kilograms times meters per second, so our change is just negative 2210. And if we wanted to make that in labels of impulse, that is going to be Newton seconds. Okay, so that's going to be our impulse that we're going to be using. And now, so let's do this, F delta T, so our impulse equals that. Now we want to figure out our forces in scenario 1, which would be the gentle stopping, and scenario 2, which would be the more abrupt stopping. Okay, so we'll have F times our 21 seconds is going to be equal to negative 2210 Newton seconds for scenario 1. And scenario 2, we will have F times 3.8 seconds is equal to negative 2,210 Newton seconds. Okay, so we're going to divide these out here, and we will get our answer for both of them. Okay, so for scenario 1, we get a force of 105.24 newtons. Okay, so then for scenario 2, we get 581.58 newtons. Okay, so then we're going to ask ourselves here, analyze this a little bit. Does it make sense? Do I have a smaller time and a larger force? Yeah, so our time went down from 21 to 3.8, just like above, and our force went up. Okay, so a shorter time is going to equate to a larger force. Okay, so this would be our linear momentum. Let's check another problem. So now we have two cars traveling. We have a 770 kilogram car and a 1500 kilogram pickup truck. We got the car that's going 13 meters per second. So this is a collision scenario. Okay, the collision lasts 0.8 seconds, during which the impact force is 6,000 newtons. Okay, so what's the impulse in the scenario, and what's the final momentum for each vehicle? What is the final speed for each vehicle? Okay, so let's see what we can do here. Okay, so let's find our momentum for the car, and then the momentum for the truck initially. Car here, and truck here. Initial momentum for both of these. So for the car, we're going to have a 770 kilograms times 13 meters per second. And then the vehicle, or the truck, excuse me, the truck is 1,500 kilograms. And its speed is 8 meters per second. They're both going to the right here. Okay, so both velocities are going to the right for both of these. So they're going to hit each other, and then we're going to see what we get afterwards. So we don't know what the final momentum is for either one of these, but that's what we're going to find. So let's put initial momentum in our calculator, so we get for that. So initial momentum for these. So for the car we get 10,010. So 10,010 kilograms times meters per second. And for the truck, we get 12,000 kilograms times meters per second. Okay, so now this one is worded a little bit differently than the last one. So it says, what is the impulse in the scenario? Well, remember, impulse is just force times change in time. And in the problem, or in this question here, we are given an average force of 6,000 newtons in the scenario, and then the time of the impact is 0.8 seconds. So we're given some information that we can just use to figure out our impulse. So A, the impulse, is just going to be, all right, F delta T, which is 6,000 newtons times 0.8 seconds, which is 4,800 Newton seconds. All right, so now we have this. So that's the impulse, which is going to be the same on both of those. So remember I talked about that a little bit ago. The impulse is the same in a collision. Okay, so that car hits that truck, the impulse on that is going to be the same as the impulse on that. The thing that's going to change though is our final momentum. Okay, so momentum depends on the mass. So if you have a less massive object, then there's going to be a greater change of momentum than the much more massive object. Okay, so let's check it out. Let's see what we can get here. So we're going to use this for our impulse for both of these. Okay, so this will be your F delta T, which is just impulse, is 4,800 Newton seconds for both of these. But we have to pay attention to the direction of the forces here. So the impulse on the car to the truck is going to be going that direction. Right? So the truck is going to have a positive impulse on it because something's hitting it from the back end, which matches up with the velocity here. Now the impulse on the car, so that's going to be from the truck. So that's going to be going that way because the truck is here hitting a force on the car, or impulse on the car going back that way. So really the impulse on the car should be negative. Okay, so that's what's a little bit different in the scenario. So let's find the final momentums here with these impulses that we have. So for B, I have an impulse of negative 4,800 for the car, and that's Newton seconds. Initial momentum is, we need final momentum here. Final momentum minus initial, so that's 10,010 kilograms times meters per second. So we're just going to add 10,010 to both sides. And that'll give us our final momentum. That will cancel out there. The units will give us kilograms times meters per second. So our final momentum of the car is 5,210 kilograms times meters per second. Okay, so the car slowed down after it hits the truck, which makes sense because the truck is more massive. So let's look at the final momentum of the truck here. So our impulse, 4,800 Newton seconds. That's going to be equal to final momentum minus initial momentum, which is 12,000. Okay, so similarly, we're just going to add this value to both sides. Alright, so add 12,000. Alright, that'll take care of that. So we'll have 12,000 plus 4,800, which gives us a final momentum of the truck of 16,800 kilograms times meters per second. So that makes sense because the car is pushing on the truck. That would increase its momentum, which would increase its speed. So now the last piece here, we actually have to find the speed of both of these. Okay, so our car is 770 kilograms and the truck is 1,500 kilograms. Let's find our final speed. So we can break apart momentum. Remember, momentum is just mass times velocity. In this case, we're doing final velocity. And we just used the masses of each of the vehicles that were given. So we would have a 770 kilogram times final velocity equal to 5,210 kilograms meters per second. Okay, so let's set this next one up. So we have a 1,500 kilogram truck times this final velocity is equal to 16,800 kilograms times meters per second. So we just need to divide out these masses here to get what we want for our final velocity. Okay, so we'll divide by 1,500 here. So let's do that and see what we get for our final velocities. So for the car, we're going to have a final velocity of 6.77 meters per second. And for the truck, we're going to have a final velocity of 11.2 meters per second. Okay, so let's compare those to our original velocities. The car should be slower because its final velocity went down, and the truck should be faster because its final momentum went up. So we can see originally the car was going 13 meters per second, so that slowed down like we thought. And originally the truck was going 8 meters per second, which went to an increase to 11.2 meters per second. Okay. So here are a couple of linear momentum and impulse problems, and next we're going to be jumping to angular momentum and angular impulse. So in the second video, I'll be working through angular momentum and angular impulse, so please check that out if you want to look at those types of problems. Thank you. So if we think about when we worked with angular systems before, we have to consider the linear qualities of the angular system, and then we also have to consider the angular qualities of that system. So if we think of linear velocity here, okay, so if we think about that, linear velocity depends on how far you are from the center, okay? And then if we think of angular velocity, that is the same throughout the object, okay? So we have to relate linear and angular systems together when we're thinking about angular systems in general. So linear momentum is going to be constant unless we have extra torques working on it. So say, for example, you're playing that quarters game, okay, with your friends, and that quarter is rotating. If nobody touches that quarter, then the linear momentum is going to be constant. If somebody gives it a kick or flicks it, then that is going to add to that linear momentum, and it could increase the speed, okay? But we're talking about things that are constant here, just to simplify it a little bit. So let's say that nobody is doing that. Okay, so nobody is pushing on that quarter. So that is going to have a constant momentum, and it's going to have a constant velocity. Okay, so momentum is mass times velocity, right? So the mass is not going to change, so it's going to have a constant velocity while it's spinning. If we forget about friction, right? So friction would be working against it, but we're not going to consider that here because it complicates things. So angular momentum. All right, so that can change a little bit. Linear momentum does not change, but angular momentum can change. Okay, and why is that? Why do we think angular momentum can change? What did we talk about with angular systems in the last chapter? All right, well, let's consider a diver. So the center of mass for the diver is right there, and then the diver jumps and starts to curl in a ball. So what is going to change when that diver curls in a ball? Well, think about this. When we jump, we have a mass that's out here and a mass that's out here. Well, that is going to deal with inertia. All right, so when the diver starts to curl in a ball, the diver essentially reduces the inertia, which makes it easier to spin. Okay, so we're spinning in the air, and then we get close to the water and we extend, and we have we have more inertia, which slows the diver down. So the reason angular momentum can change is because we have to consider the inertia of the person or of the object. So angular momentum uses the moment of inertia. And if we remember what moment of inertia was here in general, that is labeled with I, and that's mr squared. It depends on what the object is, but I stands for moment of inertia, okay? And that depends on the object's mass and the way the mass is distributed about the axis of rotation. So mass and radius from axis of rotation gives me that moment of inertia, okay? Just a little bit of a review from last section, okay? So we have angular momentum that goes along with that, and we have angular impulse. Okay, so the angular momentum is written with a capital L, and that involves the moment of inertia and angular velocity. If we remember angular velocity, that's measured in radians per second normally. If we have revolutions per second, then we can multiply that by 2 pi to get it to what we want. And the moment of inertia is, since it's mass times radius, it's kilograms times meters squared. Okay, so then our angular momentum is going to be kilograms times meters squared per second. So if we take our angular momentum, we know that like in our last scenario, we're going to have an angular impulse. So the impulse theorem, the angular version, it's called angular impulse angular momentum theorem. Okay, so that now involves torque. Okay, So it's torque times change in time times our change in angular momentum. Okay, so some other ways that we could write this, we could have torque delta T equals change in angular momentum. And if we remember, angular momentum from up above is equal to I omega, which is your angular velocity. And we can write this, or this rather, this would be I omega, so we can write this as torque delta T equals I times change in angular velocity. That would be another way to write our impulse momentum, or angular momentum theorem. This one might be a little bit more helpful, so I'll write that down below here so we can have that in our notes. So torque delta T equals moment of inertia times change in angular velocity. Okay, this one might be more helpful because sometimes we're going to be looking for a final angular velocity or an initial angular velocity. Okay, well, we could also be looking for a torque. And I didn't write the equation for torque down, but if we remember, torque is going to be a force times a lever arm or some kind of radius, and if we have that on an angle, then we have to include the sine of that angle. Okay, but in general here, torque is just going to be force times radius, so we could figure out a force or a radius or a torque if we were using that. Okay, so these two relate together. So we have lots of things going on here. So let's look at a few problems. Okay, so we are looking at angular impulse, and we're going to be looking at the angular impulse angular momentum theorem. So we will write those off to the side here. So angular momentum, all right, that is given by L, and that is going to be equal to the moment of inertia times the angular velocity of the object. Okay, so we have to figure out or know what the inertia is of the object, which we could figure that out, or it might be given. And then we're going to have to figure out what the rotational velocity would be in radians per second. Okay, so that would be our angular velocity. So let's look at the scenario above here. So we have an ice skater spinning at 2.5 rotations per second, and we are given we're given a moment of inertia of 0.5 kilograms times meter squared. What is the angular momentum? And then at the conclusion of the spin, the skater slowly and dramatically stops, or slows to a stop over 3 seconds by dragging the toe on one ice skate. What's the value and sign of angular impulse on the skater? What average torque did the ice exert on the skater? So that ice, or the friction from the ice, is what's slowing the skater down. So we have a lot of things here that we're looking for. So let's see if we can find this first, and then we're going to write out our angular impulse and angular momentum theorem here in a second. Okay, so originally the skater is going, so that's the initial angular velocity. That's 2.5 rotations, or also revolutions is like what I like to say, per second. So 2.5 revolutions per 1 second. If we remember how to convert that from previous lessons, then we can do some tracks. So 2.5 revolutions in 1 second. And we have to think about radians here because we want to convert that to radians per second. Every revolution we're going through one entire rotation of a circle. And a circle is 2 pi radians. So we have 1 revolution is equal to 2 pi radians, right? So that dimensional analysis there, our revolutions would cancel and we'd be left with radians per second. Now I don't want this in terms of pi. It might be best to drag that through the entire time, but I'm going to round this to get us a decimal to carry through. So my initial angular velocity is going to be 15.71 radians per second. So that's our initial angular velocity that we are having, or that our skater has. Okay, so we need to use this to calculate our angular momentum at that time. Okay, well, angular momentum is given by moment of inertia, which in our problem or our scenario is 0.5 kilograms times meters squared. And then we're going to take that times our angular velocity, which is 15.71 radians per second. Okay, so our angular velocity is going to be 7.85 kilograms times meters squared per second. So that would be the answer to our first question. Our angular momentum that we have at the beginning of the scenario is 7.85 kilograms times meters squared per second. So next, we put our toe on the ground, or the skater puts their toe on the ground and slows to a stop. So we're looking for that impulse. Okay, so remember, impulse is torque times change in time equals my moment of inertia times change in angular velocity here. And then our other equation that we could have is that angular impulse, angular momentum is equal to change in our angular momentum. So this one might be the easier one to use here, just because we don't really have to figure out a final angular velocity or anything like that. We're just looking for our impulse here. So impulse is going to be change in angular momentum here, and we found our initial momentum to be 7.85 kilograms times meters squared per second. What's the final angular momentum here? Well, the skater is going to come to a stop in 3 seconds, so we know that that's just going to be moment of inertia times final angular velocity, which is just going to be a 0 kilogram times meter squared per second. So we don't have to do a whole lot of work there, just because we know it's going to be 0. So if we're trying to find angular impulse, which is torque delta time, or torque change in time, that's going to be 0 minus 7.85 kilograms times meter squared per second. So it's just going to be that negative 7.85 kilogram times meter squared per second. And the way we write the label for angular impulse is not this. We have to change it, okay, because we know that torque is in Newton meters and then time is in seconds. So that Newton meters per second, or Newton meters times second, so that Newton meters times seconds is the label for angular impulse. Okay, so that would be our next question, or our second question. So the final question that we're going to be looking at here is, what is the average torque that is exerted on the skater by the ice? So what's the torque that's causing the skater to stop? We are given a time value of 3 seconds. So now we can just take that time value and plug it into our impulse here, and then we can find that torque. Okay, so let's do that. So if we divide both sides by 3 seconds, then we get 2.62, and that will be a negative. So torque is going to be a negative 2.62 Newton meters, if we remember from torque before. So there's a negative 2.62 Newton meters exerted on the skater, which is causing that skater to come to a stop. Okay, so we related angular momentum with the angular impulse, which is time and torque, and we used the time that we were given to find the torque exerted on the skater to come to a stop. So for the last example here, we're looking at a DVD player rotating. So the DVD rotates at 25.5 rotations per second when we're looking at the inner edge, okay, and it is rotating at 10.5 rotations per second when we're looking at the outer edge. So what is the change in angular momentum as the disc is read from the inner edge to the outer edge? So let's label the inner edge as our initial momentum, angular momentum, and let's label the outside edge our final momentum. Okay, so remember, our angular momentum is the moment of inertia times the angular velocity. Okay, well, with each of these we have an angular velocity that's given, so we can write that off to the side if we want to. we have an initial angular velocity and a final angular velocity. And if we remember in the last problem, if we want to go from rotations or revolutions per second, we just multiply it by 2 pi, and that's going to get us to radians per second. So we're going to write those down below, but I'm going to have these values taken times 2 pi. So our initial angular velocity is 160.22, and that's radians per second. And our final angular velocity is 65.97 radians per second. Okay, so what we're looking for here is just our change in momentum. Okay, so that would be change in angular momentum. And if we remember from our last scenario, or from our equations, that could also be written as moment of inertia times change in angular velocity. So this is pretty easy to get, and we have our moment of inertia up above here. Okay, so let's just kind of plug that in. So change in angular momentum is going to be equal to 2.7 times 10 to the negative fifth, and we're working in scientific notation here. That's a fairly small number. If you put that in your calculator as exactly as it is there, then you should be okay. And then it's going to be final minus initial, because that is what delta omega is. So 65.97 minus 160.22. Okay, so simplify this a little bit. We're going to put this in our calculator, and we'll save the units for the end here. So putting this in your calculator, you get negative 94.25. And then we'll finish this out. And we get negative 0.0025 kilograms times meters squared per second for our change in angular momentum. If we wanted to do scientific notation just to kind of follow suit there, we'd move our decimal place 1, 2, 3, so it'd be between the 2 and the 5. So negative 2.5 times 10 to the negative third kilograms times meters squared per second. Okay, so we can see that angular momentum changes here from the inner edge to the outer edge. Alright, now you might wonder why that is. Well, think about our moment of inertia here. What's going to be different if we go from inner to outer? Right, so if we go from inner to outer, you're going to have more mass towards the outside edge, which is going to change the number. So we're going to have a greater value minus a lesser value from the inside to the outside of the DVD. So these were a couple examples on angular momentum and angular impulse. So hopefully these help you out in your lesson. And thank you for watching.